So in this lecture what we will learn is we will learn about the Mohr circle for plane stress. So in the previous lecture we talked about how we can find the stresses along certain orientations and also how we can find the principal stresses. And we have all those equations, but sometimes it's kind of difficult to visualize how it works. So Mohr circle is a method that we can kind of visualize how we can find the maximum stresses or how we can find the new stresses along different orientations. So this is why we can use this graphical method to find the stresses. And in this Mohr circle, so what we need to do is, first of all, we need to draw a axis system. So the horizontal line will be our normal stress and the vertical axis will be our shear stress. Okay? And then what we need to do is, so we need to find a couple of points. First of all, we need to determine what's our sigma x, what's our sigma y, and what's our shear. Okay? And then what we need to do is, after we find them, we need to find these points x and y. And x is given here, which is sigma x and minus tau xy. And then y point is given as sigma y and plus tau xy. So just be careful. So when you find this x point, it is sigma x and minus tau xy. So you need to correctly find the stresses in the with our positive signs convention, and then just plot this x and y. And then basically you will draw a circle that contains these 2 points. And when you have this circle, and C will be your center, and this C will be equal to your average stress, which you can find it by sigma x plus sigma y divided by 2. Okay, so this is your C, and this radius, it will be given by this equation, which is equal to sigma x minus sigma y divided by 2 square plus tau xy. And as you can see, this is our so as you can see, so if you want to find this R, so you need to find the point from A to C, sorry, not to C, so from here to C, and then it's equal to sigma x minus sigma y divided by 2, because it's the half of this difference. And then we have shear stress square. So either you can find your center and you can find your radius and draw your circle, or you can find these 2 points x and y and then draw your circle. Okay? And then after you draw this circle, so whenever you rotate your stresses on this plane stress condition between these axes x and y, so what you will do is you will just move through this circle. And if you look at this graph, so and if I ask you what's your maximum normal stress, you can see that your maximum normal stress is at A. Okay, so which means that if I want to rotate my axis system from whatever I have right now, from xy to this axis system, what I need to do is I need to rotate this line by 2 theta p. Okay, and in real life, so what you need to do is, if you want to find your principal stresses, you rotate by theta p. So this is the difference. So in actual configuration, you need to rotate it by theta p, and in this graph, you need to rotate it by 2 theta p. And then you will end up with x will become A, and your y will become B. And x will correspond to your maximum stress, and your y will correspond to your minimum stress. So this is really effective method. And so also, if you want to find what's your maximum and minimum stresses, so basically it's equal to your average plus R. Okay, and if you want to find your minimum, it's your average minus R. So as long as you can get this graph, it's very convenient to find these locations of A and B. And this angle from geometry, you can find that it's equal to tangent 2 theta p is equal to this length divided by this length. Okay, so which is equal to 2 tau xy divided by sigma x minus sigma y. Okay, so by doing this, you can find your principal angle. Okay, and by using this equation, you can find your principal stresses. And just be careful. So here I have my x and y points, and if you rotate counterclockwise to reach your principal stresses, on this one you also need to rotate counterclockwise. And if you rotate clockwise on the Mohr circle, you also need to rotate clockwise in the real stress configuration. Okay. So the direction of rotation OX to OA is the same as CX to CA. Okay. All right. And with Mohr circle, we can also find our stresses at any other angle. For example, let's say again we contract our Mohr circle. This is our normal stress and this is our shear stress. And let's say that in this configuration, you find your point X and you find your point Y. Okay, so we are looking at this configuration XY system. Okay, and then if you rotate it by theta, and if you want to find your new stresses, so basically all you need to do is you need to rotate this by 2 theta, and now this will become your X prime and this will become your Y prime. So by doing this, you can, and then you can use geometry to find these points, and then you can get all your stresses. Okay, and an important point, just don't forget that if you rotate in XY system by theta, on this system you need to rotate by 2 theta. In Mohr circle you need to rotate by 2 theta. Okay, and then after that, as long as you can find your X prime and Y prime coordinates from geometry, you can determine all your stresses. And again, if you want to find your principal stresses, in this case what I need to do is here I need to rotate by 2 theta p, and in this one you need to rotate by theta p. Okay. And what we will do next is we will just look at some cases and we will try to construct our Mohr circle. Okay, and the basic one is intention experiments. So you have a sample, and then if you just apply some load. So from here I'm looking at this configuration. So my X is along the load applied and my Y is perpendicular to that one. And in this case, if you calculate your stresses, what you will find is you only have normal stress, which is equal to P over A, and your shear and other normal stress is equal to 0. So in order for me to construct my Mohr circle, I will find my points. So I have X point, and in this case it's equal to P over A and 0, since shear stress is 0. And I will also find my Y point, which is given by 0 and 0. So if you draw your Mohr circle, so again this is my normal stress and this is my shear. Okay, and my X corresponds to here and my Y is there. So if you draw your Mohr circle, this is how it looks like. Okay, and in this case, so since I'm on XY plane, so this is already my principal plane. Okay, and but if you want to find your maximum shear, so what you need to do is you need to rotate this to D and E points. So this is where your maximum shear is. Okay, and so here I need to rotate 90 degrees, which means that in real configuration I need to rotate it by 45 degrees. So if you rotate 45 degrees here, you need to rotate 90 degrees there. So X becomes D and Y becomes E. Okay, and then if you find your shear, so basically you will get, so it will be your shear will be equal to your R. Okay, and in this case you can find that your R is equal to P over 2A. Okay, and if you are on this plane, so just also make sure that, so I have my shear stress, but I still have also my normal stress. So my normal stress will be equal to my average stress. Okay, so the point D, so if you write the coordinates, it will be sigma average and minus shear maximum. Okay, and this point it will be also my average and this time my shear maximum. Okay, so with this one I can find that, so my XY system is already my principal stresses, and you can also guess it because your shear is 0. So on the principal axis your shear is 0. Okay, and if you want to find your maximum shear stresses, I need to rotate it 45 degrees. And then let's also look at for torsion. So if you have a member and if you apply torsion, so it only creates shear stress, and the maximum shear stress is given by Tc over J. Okay, and in this case there is no normal stress, so your sigma x and sigma y are both equal to 0. So which means that if you find your points x, so now it is 0 and minus Tc over J, and if you find your point y, now it is 0 and Tc over J. So next, if you draw it, so my x point is 0 and minus Tc over J, and your y point is 0 and plus Tc over J. So basically I'm on this plane. Okay, and then again my average, this time it will be equal to 0. And you can also find your R, which will be equal to Tc over J. Okay. And if I ask you, what's your principal stresses this time? So basically we want to come to A and B points. So which means that here I need to rotate it 90 degrees. And it means that in real life, you need to rotate it by 45 degrees. So this X, it becomes A, and your Y, it becomes B. And if you do that, if I rotate it, so the point A, so it will be also equal to Tc over J and 0, okay? And your point B, it will be equal to minus Tc over J, okay? And if you find them, so this will be the data, okay? So your X will be positive and your Y will be in compression, and your shear will be equal to 0 if you rotate it towards 5 degrees. Okay. So this is kind of, it gives an opportunity for us to visualize how this stresses works when you rotate them. So we will solve a couple of examples. So first one is, so let's say that they give us this plane stress condition and they tell us what are the stresses. So we want to construct our Mohr circle, we want to determine our principal stresses, principal planes, and maximum shearing stress, and the normal stress at that maximum shear stress. Okay. So the first one is we need to construct our Mohr circle. So in order to construct my Mohr circle, what I need is I need my X point. Okay. And in order to find my X point, first I need to know my stresses. So my sigma X is 50. My shear is 40. So it's 50 and minus 40. And then I need my Y point. It's sigma Y and tau XY. And in this case, this is compression. So this is why I need to put minus 10 and then 40. Okay. And then after that, I can draw. So I know my point X, I know my point Y. So as long as I know the coordinates, I can draw this and I can draw my circle. And you can also find your average, which is equal to sigma X plus sigma Y over 2. So it's 50 plus minus 10 divided by 2. So it's 20. So it gives you this location. And then you can also find your R. And when you find your R, either you can use this graphical method. So what I can do is I can find what's distance from distance of Fx and Cf. Okay. And so this X is 50 and this is 20. So which means that the distance of Cf is 30. So it's 50 minus 20, which is equal to 30. And if you look at Fx, so basically it's my shear stress, which is equal to 40. So from there, you can calculate your R, which is equal to 50 megapascal. So this is how you can calculate graphically, or you can just use the equation, which is given here, and you will get the same answer. Okay. So either you can use this equation or you can use graphically. So, though I recommend you just using this equation because I think it's kind of simpler. Okay. And after I get this information, next is I want to find where my principal planes and my principal stresses. So if you look at that, so where is your principal stress? So A is my maximum stress and B, it gives me my minimum stress. Okay. And so which means that if you want to find your A, so what I need to know is I need to know the distance from O to C and then C to A. And C to A is basically my R and O to C is my average. So basically my maximum is equal to my average plus R, which is equal to 20 plus 50. And it gives you 70. And then if you want to find your minimum, so basically it's equal to my average minus R, which is equal to 20 minus 50, and it's minus 30. Okay. Or graphically, so if you look at this, so if you want to find your B, okay, and so my B is equal to OC, which is my average, minus BC, which is my R. Okay. All right. And then what I need to do is I need to also find my angle, okay? And if you look at angle, so I need to rotate it. So I need to find this angle. So the angle between CA and CX, okay? And it will be equal to 2 tangent theta p. And so here I need to rotate it. So if I want to move X to A, I need to rotate it counterclockwise. So this is why I also rotate it counterclockwise, okay? And then if you need this angle, so tangent of this angle, which is 2 theta p, should be equal to fx divided by cf. Okay, so tangent to theta p should be equal to fx divided by cp. So this distance divided by cf, so which is equal to 40 divided by 30. So from that you can get 2 tangent theta p, and then if you just want to get the angle, you just divide it by 2. So basically you get this angle. Okay, and this is how it looks like. So if you go from here to there, so this is my tangent theta p, so while this is tangent to theta p. Okay, and then you need to know your stresses. So my x becomes a, and a is equal to 70 megapascal, and my y, it becomes b, and b was minus 30, so it is tension in 70 megapascal, and this is compression in 30 megapascal. Okay, so this is how it looks like. And then next is I want to find my maximum shear stress. So if you look at this graph, so what my maximum shear stress is, either I need to rotate x to e, or I need to rotate x to d. Okay, and so if I want to rotate from x to d, so basically this is my tangent to theta p, and I need to add 90 degrees. Okay, so which means that if you work in real coordinate system, so I can find that my theta s should be equal to theta p plus 45 if I want to go to this point. Okay, and if you do that, you can find that your theta s is equal to 71.6. Okay, so which means that from here to there it will be equal to 2 times theta s. Okay, and then what's my maximum shear stress? So maximum shear stress is equal to R, and basically it's equal to 50 megapascal. And in this case you might ask, like, why is not minus 50? So for shear, generally we just use the positive value, because in generally for tension and compression, some materials they have different properties, but for shear it really doesn't matter whether you have plus 50 or minus 50. So the material does not have different strength values for the positive or the negative values. Okay, and also when you move your x to d, so what's your normal stress? So the coordinates of my point D is basically my average, okay, and then minus tau xy. So if the normal stress when your shear stress is maximum is given by sigma average, and we already calculated that it's equal to 20 megapascal. Okay. So which means that, so this is the coordinate system we started. So if I rotate it by theta p, I get my principal stresses, and if you rotate additional 45 degrees, you get your maximum shear stress plane. And when you get your maximum shear stress plane, so your Tmax is equal to R, and the normal stresses are equal to your sigma average. Okay. All right. So this was just one example, and what we'll do is we will solve one more to understand it better. Okay. So this is a similar question. So the stresses are given. So first we want to find the principal planes and the principal stresses, and then in the second part what we want to do is we want to find stresses when we rotate this element by 30 degrees counterclockwise. So normally we provided the equations, so you can just use them. But here we want to use our Mohr circle to find these new stresses when you rotate the element by 30 degrees. Okay. So first step is again constructing our Mohr circle. So I need to know my stresses. So sigma x is basically 100 megapascal. Your sigma y is equal to 60 megapascal. But shear, just be careful. This time it will be equal to minus 48 megapascal, because my positive sign normally it should go up. So which means that if you find your x coordinate, it will be equal to 100 and minus 48, so it makes it 48. And your y, it becomes 60 and minus 48. So when you construct it, so this is my x, so it's 148, and this is your y, which is equal to 60 and minus 48. So you can form this circle, or you can also find your average, which is equal to 100 plus 60 divided by 2, which is equal to 80 megapascal. So this is point C. And then you can find your r, either your graphical method, or you can use this equation, and at the end you will get it as 42 megapascal. Okay. All right. So which means that I find my average, I find my R, and I know my points X and Y. So now I want to find my principal stresses. So in order to find them, so I have my X and I will rotate it towards A. And this time I'm rotating clockwise. So my X will come to point A and my Y, it will come to point B. So which means that I need this angle. Okay. And what is this angle? So tangent 2 theta P should be equal to RF divided by CF. Okay. And what is RF equal to? So RF is equal to 48. Okay. What is CF equal to? CF is equal to CX minus C average. Okay. And if you do that, so if you calculate it, so tangent 2 theta P is equal to XF divided by CF, okay, which is equal to 48 divided by 20, which is equal to 2.4. So from there, 2 tangent theta P is equal to 67.4. And if you divide by 2, you will get it 33.7. And it's clockwise. So which means that I need to rotate clockwise my element by 33.7 degrees to reach this principal plane. And when you reach it, so my X, it became A. So it became the maximum, which is equal to my average plus R, which is equal to 132. And then your minimum stress is your average minus R, which is equal to 28. So here, since X became A, so this is my maximum stress, and your Y, it became B, so you have the minimum stresses. So it's how it looks like, your principal planes. Okay. And the second one is, I wanted to rotate this 30 degrees clockwise. So I have this XY plane, and which means that on more circle, I need to rotate it 60 degrees. Okay. So this is my XY plane, and now X becomes X prime, and your Y becomes Y prime. Okay. And so this is my new axis system. So what I need to do is, I need to find this coordinates of this new system. Okay. And this is how it looks like. So I have my XY system, and now I need to rotate it 30 degrees, and in more circle, I rotate it by 60 degrees. Okay. And I want to find the coordinates of this system. So which means that I need to know K, and I need to know this new shear stress, X, the distance from X prime to K. Okay. And it seems like it's good if I find this angle phi, and basically this phi is equal to my 2 theta P plus 2 theta, and I need to subtract them from 180. So which means that if you want to find your phi, it's equal to 180 minus 60 and minus my 2 theta P, which is 52.6. Okay. And if you want to find the coordinate of this system, so what I can say that my sigma x prime, okay, so which means that basically I'm trying to find O to K, okay, should be equal to my distance from O to C, which is my average, minus the distance from K to C. Okay, so it's OC minus KC. Okay, and O to C is I already calculated that it's equal to 80. Okay, and this is R, so this KC is equal to R times cosine theta. Okay, so since this is my R, okay, so the distance from K to C is equal to R times cosine theta. And if you want to find your sigma y prime, so what I need to know is I need to find the distance from O to L. And if you look at it, so basically it's equal to O to C plus C to L. And O to C is my average, which is 80, and C to L is equal to R times cosine theta. Okay. And then if you want to find your shear, so since this is your R, if you want to find your shear, it's equal to R times sine 52.6. Okay. And if you calculate them, so these are the stresses that you get. So you get your sigma x prime is equal to 48, your sigma y prime is equal to 101.6, and you get that your shear is equal to 41.3. Okay. And again, so this is actually, you should have minus, because the coordinates of this x prime, it will be equal to sigma x and minus tau xy. Since this value is positive, your tau xy should go to the other direction. So if you plot it, so this is my sigma x, okay, and my shear should be minus direction, and this is your sigma y. Okay, and so this is why this Mohr circle is a very good method where we can visualize what happens to our stresses when we rotate them. And you have all the equations for rotations, so you can, if you know your angle, like how much you rotate, you can find your stresses. But still, this one kind of provides us a good idea, like what happens if I rotate this counterclockwise to reach A, or I can also rotate it counterclockwise to reach B. And by visualizing this, I can determine what are my stresses easily. So in this class, we will mostly work on either plane stress or plane strain conditions. But when we consider the material, actually it's a 3D material. So we need to be aware of what happens in general state of stress. And I will not really go into details, but in general stress state, so what we have is, we have the 6 components. So we have sigma x, sigma y, tau x, y, plus we can also have sigma z, tau x, tau yz, and tau zx. And if we do a similar analysis where from the equilibrium, what we will end up is, we will end up there will be some, we will still have this principal axes and principal planes in 3D. So if I have my stresses on XY system, these 6 components, if I rotate it to certain orientations, what I will get is, I will get this normal stresses only. So I will have sigma A, I will have sigma B, and I will have sigma C. Okay, and in generally what we do is, so we kind of so after you find them, so these 3 stress components, then we can use our Mohr circle in 3D. Okay, and when we are using Mohr circle, so what I need to do is, I need to plot this my principal stresses. So I will find my sigma A, I will find my sigma B, and I will find my sigma C, and I will plot them. And now what I have is, since this is 3D, I can rotate my element between A and B. Okay, so if you rotate your element A and B, so basically this was my sigma A and sigma B, so I'm rotating my element in this Mohr circle. Okay, but I can also rotate my element between B and C, so I have another Mohr circle. And finally, I can rotate my element between A and C, so I will have this another circle. So which means that if we use our Mohr circle in 3D, so instead of getting one Mohr circle, we will get these 3 circles. Okay, so between each axis, I can get this 3 stresses. Okay, and similarly, so since this is my normal stress and this is my shear stress, what you will see here is, so when I find this my principal stresses, they don't have any shear stress. Okay, so this is a definition also of my principal stresses and planes. They don't have any shearing stresses. Okay, and again, if you can determine what are your stresses, so I can rotate them between these new circles, and I can determine what are my stresses are there. Okay, and now if I look at this graph, what I will see is, what is my maximum shear stress? Okay, so it's clear that my A is my maximum normal stress and my C is my minimum normal stress. And if you look at this, I will see that this point, it corresponds to my maximum shear stress. So the definition of my maximum shear stress is equal to 1/2 times sigma x minus sigma mean. And this is the absolute maximum. And if you only rotate it between A and B, you can see that you also have another shear stress there. And if you rotate it between B and C, you only have this shear stress. So these shear stresses, we call it in plane shear stress. Okay, and you can find it by sigma A minus sigma B divided by 2. But if you are looking at the absolute maximum, what you need to do is, you need to find your 3 principal stresses, and you need to determine which one is maximum, which one is minimum, and you need to use this equation. Okay, so we will not gonna deal with 3D stresses, but we need to apply this knowledge to our plane stress. Okay, and in order to use our plane stress, what we need to know is, and actually before we do that, so let's look at a general case again. Okay, and let's say that you find your point A, and then you find your minimum. Okay, and if you find them, and let's say that one of your maximum stress is positive, and one of your and the other principal stress was negative value. So which means that A is on this side and B is on the other side. Okay, and then you know that due to your plane stress, so your other sigma z is equal to 0. So my other principal plane stress is at the origin. So if you draw your plane stress configuration, okay, this is your circle, and then you have this additional two circles. Okay, and then in this case, the principal stresses you find at A and B, so basically they correspond to your maximum and minimum principal stresses as well. Okay, so which means that in this case, if you find your shear, so all you need to do is you need to find your sigma max, you need to find your sigma b, since you are already on this circle, and you just take it half. Okay, and then you can find that your maximum shear stress is, again, you need to rotate it by 45 degrees with respect to the principal plane. Okay. So this is how it looks like. So if you find your A and B, so all you need to do is you need to rotate it by 45 degrees. Okay, so this is like what we did before, so nothing new, but we need to be careful when we find our principal stresses A and B, and if both of them have positive or both of them are negative. Okay, so in this case, so you will construct this Mohr circle. When you construct your Mohr circle will look like this. So you have A and B, and you will find it somewhere there. Okay, but since we are in plane stress, I know that my third principal stress is 0. So which means that actually I have these two additional Mohr circles. Okay, so this is why when you find your shear stress, if you only find your shear stress considering this circle, you will find that it's equal to from here to D, and it will be your maximum shear stress in plane. Okay, but if you want to find your absolute maximum shear stress, so basically what you need to know is you need to know this distance from 0 to D prime. Okay, and if you look at this, so basically since this is 0 and this is my sigma maximum, all I need to do is, if you want to find your shear, it's equal to 1/2 of sigma max. Okay, and this time if you want to reach your sigma max, instead of rotating between A and B, I need to rotate between A and Z. So I need to rotate it 45 degrees between A and Z planes. Okay, but this is the difference. If both of them have the same sign, if both of your principal stresses are positive, or if both of them are negative, then this is the equation that I need to use for plane stress. And also another thing that we need to consider is, so we need to determine when these materials fail. Okay, and so sometimes these materials will undergo very simple loading, so you will just have maybe like under tension you will just have one stresses, but other times they will undergo to very complicated stresses. Okay, so but what we want to do is, so you can take a material and you can do a failure test, like you can do tension or compression, and you can also do maybe a shear test. Okay, and you can get some information. So the idea is how can I use this simple knowledge that I can get from either tension or shear stresses, okay, and how I can predict my failure of the material. Okay, so people, they develop different theories, and we will just quickly summarize what they are. So the first one is yield criteria for ductile materials under plane stress. Okay, so if you have a ductile material, what you want to do is you want to look at your shear stress. Okay, and the first one is we call maximum shearing stress criteria. So, and what it says is your structural component is safe as long as the maximum shear stress is less than the maximum shearing stress in a tensile test specimen. So what if you take a material and if you do tensile test, okay, you can find your shear stress, which will be 45 degrees difference from your x and y axes. So your shear stress in tensile test will be equal to your sigma y divided by 2. And this is what I showed before earlier when we constructed our Mohr circle. So what it says is as long as your shear stress is less than this value, which is sigma y over 2, you will be safe. Okay, and if your shear stress is increased, then your material will be failed. Okay, and again, if you want to find your maximum shear stress, if you find your sigma A and sigma B, so if you find your maximum and minimum stresses, if they have the same sign, basically you need to just find the maximum values. Okay, and if they have opposite sign, then you need to take the differences between them and divide by 2, and then you need to compare it with sigma y over 2. So for example, if this is your maximum stress, okay, so after you determine it, you just divide it by 2, and if it is less than sigma y over 2, you are safe. And if they have the opposite sign, so you need to take the differences between your principal stresses and you need to divide by 2, and it should be less than sigma y over 2. So this is the yield criteria for ductile materials by using the maximum shearing stress criteria. And then people did some experiments and they find that that one is not always working. So then they came up with another idea. They say that instead of just looking simple shear stress, let's calculate the kind of this distortional energy, okay, that's stored in the material. So when you deform a material, so you undergo some change in volume, and then you also undergo some change in shape. So this is why if you find this distortional energy and you're saying that it should be less than some parameter, okay, and then so basically what they came up with is this formula. So if you find your principal stresses, again we are talking about plane stress, so basically you get sigma A and sigma B, and then you just calculate this value, okay, and as long as this value is less than the square of your sigma y, you are safe, okay. If this value is larger than your sigma y square, then your material yields. Okay. So these two, they are generally used for ductile materials. So brittle materials, generally they fail from normal stress. So for them, it's kind of very straightforward. So all you need to do is you need to find the ultimate strength of your material, and then you need to find your maximum stress. And if your maximum stress is less than your ultimate stress, you are fine. If it exceeds your ultimate stress, or sometimes we can also use your yield stress, your material fails. Okay. So just to summarize, so we have two conditions for ductile materials. Either you can just look at your shearing stress, or you can calculate this value, so sigma A square minus sigma A minus times sigma B plus sigma B square, and it should be less than sigma y square. Okay. And then for ductile materials, generally we just look at the maximum normal stress, and if it is less than your ultimate stress, you are fine. If it exceeds it, then it fails. So what we will do is we will just show an example to understand these concepts better. Okay. So we have a material, okay, and the yield stress is given as 325 megapascal, and we want to use the maximum distortion energy criterion to determine whether yield occurs or not, okay, and they give different values for sigma 0, and shear stress is given as 100. And in the second part also we want to use the maximum shearing stress criterion. So basically we will use both criteria given for ductile materials to determine whether the material will fail if you apply different sigma 0 values, okay, and they change from 200 to 280. All right. So in order to solve this, so what I need to do is first I need to find my maximum and minimum values. So this is why first I find my average, which is equal to minus sigma 0, and then you can find your R, which it will be equal to 100 megapascal, okay. Since they have the same values, they will cancel each other, so it will be equal to 100 megapascal, okay. And then we will start using the values given. So first one, they select sigma naught is equal to 200 megapascal, and so from there we can find that our average is equal to minus 200, and then we can determine that our sigma A is equal to 100 and sigma b is equal to minus 300. Okay, and after we find this, then I need to calculate the criteria for the maximum distortion energy criteria. So I need to find this value, sigma a square plus sigma b square minus sigma a sigma b, and I need to take the square root of it. And if you do that, you will find that it's equal to 264. And since it's less than 325, we are safe. And if you want to find your factor of safety, so it's equal to your yield stress divided by the stress that was applied. So from here, you can find that your factor of safety is equal to 1.228. So in this case, also we want to look at what happens if we use our maximum shearing stress criteria. And so since these have the same sign, so this is minus 100, this is minus 300, so which means that your maximum stress will be equal to 0 because we are in plane stress, and I know that my third principal stress is 0, and your minimum stress will be equal to minus 300. So which means that if you want to find your Tmax, remember that when you are finding Tmax, you can use this equation, which means that 2 Tmax is equal to sigma a minus sigma b. So 2 Tmax will be equal to sigma x minus sigma min, which in this case is equal to 300, and this should be less than your sigma y. Or the criteria was given as Tmax should be less than sigma y over 2. Okay. So this is how you get. And then when you compare this, since it is less than 325, so it's also safe if you use this shear stress criteria. But if you calculate your factor of safety, so it will be equal to your sigma y divided by this value. Okay, so it will be equal to 325 divided by 300, and then your factor of safety will be 1.083. So which means that this is kind of a lower factor of safety, and if you use the maximum distortion energy theory, then it is larger. So this is a little bit more conservative. Okay, so this one gives us a little bit more availability to use different stress values. And then what we will do is we will also look at 280. And then if you use sigma 0 is equal to 280, then you can find your average. Okay, and then you can find your sigma A and sigma B. And if you find them, so again, they have both minus signs. So this is minus 180, this is 380. And then you can calculate this term, okay, and it's equal, it will give you 328.24. And since it's larger than 325, you will see that it yields, so it's not safe. Okay, and if you use your maximum shear stress theory, and you can find that your 2 theta max will be equal to basically just half of your so it will be equal to your sigma minimum. Okay, and since it's also larger than 325, it will also yield. Okay, so which means that by using these theories, so if your sigma naught is equal to 200 megapascal, it will not fail. But if you use 280, it will fail for both criteria. Okay, and if you compare for this given stresses, so this is more conservative, so you get a less factor of safety. And here, if you use this maximum distortion energy theory, you will get a larger factor of safety. Okay. So in this topic, so what we'll learn is we will learn the stresses in thin wall pressure vessels. And what we will consider is we will consider that we have a very long tube and we are considering a section. So we are kind of neglecting the end points of this pressure vessels. And so when you have a pressure, so what we will is this pressure will create some stresses. So some of the stresses will be along the sigma 1 direction, so we call it hoop stress, or sometimes we also call it circumferential stress. And then the other stresses it will create it will be longitudinal stress along this sigma 2 direction. Okay, and this is going to be all around the tube. So depending on where you select, you can get different axis system, but this longitudinal direction will be x, and we will call this y and z. Okay, And again, if you select an element on top, your sigma 1 will be equal to sigma z. And if you select your element on the side, your sigma 1 will be equal to sigma y. So depending on how you select your sigma 1, it will have different indices, but basically it will be the same stress all around this tube. So if you want to find this sigma 1 and sigma 2, what we need to do is we need to use our equilibrium equation. So if we cut the tube, okay, and if you look at this section, so what you will see is, so whenever we cut it, it should be in equilibrium. So we will write the equilibrium along the z direction, okay. And if you write it, so what we have is we have this inside pressure, okay, and pressure times area, it will give me my force due to that pressure. So if this is my P and area is, so this is my R and this is my R, so it is 2R times delta X, it will give me my pressure times area. And that force is countered by the stresses created on this tube, and it will be equal to sigma 1 times dA, and I have two of them, so it will be 2 times thickness times delta X times sigma 1. So if I write this equilibrium, what you will find is the stress along the hoop direction or circumferential stress, it will be equal to PR divided by T. Okay, so P is the pressure, R is the radius, and T is the thickness. And since generally we will assume that this R is much larger, so I mean you can use the R inside, but if the R is given at the mid plane or the top plane, so you can still use R because this is a kind of a little bit approximation. Okay, but normally the definition of R is the distance from your center up to the inner radius of the tube. Okay, and then if you cut it along the X direction, then what you will get is, so we will have this pressure, and then I will have the stress build up along the longitudinal direction. And this time, if you write the equilibrium along the X direction, so what you will get is, I have pressure inside, so I need to multiply with the area. So the area is equal to pi times r square. Okay, and then the stresses formed on this wall is, I can approximate it by 2 pi r times thickness. Okay, so it will give the area of this tube, okay, and times sigma 2. So if I write the equilibrium, what you will find is you will find that your sigma 2 is equal to PR over 2T. So what you realize is your longitudinal stress is half of your hoop stress, okay, and both of them are normal stresses. So in this case we only have normal stress, we don't have any shear. So if you draw your Mohr circle, so you will find that this is your sigma 1, which is equal to 2 times sigma 2, and your B, it will correspond to your sigma 2. Okay, so I will have this Mohr circle. But since this is plane stress, I know that my third principal stress is 0. So which means that in addition to this this Mohr circle, I have another one, and I have this large Mohr circle. So this is why if we ask you what's your maximum shear stress, so what we can do is, first, if you just consider this Mohr circle between A and B, so you can find that your maximum shear stress is from 0 to D, okay, and basically it's equal to your radius, which is equal to half of your sigma 2, which is equal to PR over 40. So your maximum in plane shear stress is PR over 40. But if you consider this large circle between O and A, you will find that your maximum shear stress out of plane, or the absolute maximum shear stress, it will be equal to from B to A, which will be equal to your sigma 2, which is equal to PR over 2T. Okay. So in this case, we figure out that our maximum shear stress for thin wall pressure vessels is equal to PR over 2T. Okay, and if you want to reach this, so I need to rotate it between O and A axes. Okay, so which means that I need to rotate it 45 degrees along the longitudinal axis. Okay, and so since the material, if the material fares from maximum shear stress, we need to use this value. Okay, because this is T max and it's equal to PR over 2T, which is equal to sigma 2. And we might also encounter some questions where we have spherical pressure vessel. So in this case, whenever you cut it, so this will be the same equation we use for the longitudinal stress. You will find that, see, due to symmetry, it doesn't matter it's either sigma 1 or sigma 2. Whenever you cut, you will always get this shape. And you will find that both your stresses will be equal to PR over 2T. Okay? And if I ask you to draw this Mohr circle, how would you draw the Mohr circle of this one? Okay? And since there is no shear, I know that these are my principal stresses. And if you plot it, basically what you will get is, you will just get this point. Okay? And since this is plane stress, my third principal stress is 0. So what I will get is, I will get this Mohr circle. And if I ask you what's your maximum shear stress, it's equal to 1/2 of your normal stress. Okay, and again here, since this is my point, I don't have any in-plane maximum shear stress, and the absolute maximum your shear stress is equal to PR over 40. Okay, and to be honest, we're not gonna really use this spherical formula, but we will use the other one often. So let's solve some examples and to apply what we learned. Okay. So here we have pressurized steel tank, and this steel tank is constructed with a helical weld. So you have this weld lines. Okay, and this angle alpha is given as 60 degrees. Okay, and the radius is given by 0.5. The thickness is given by 50 millimeter, and the pressure is given by 2.4, and modulus of elasticity is 200 gigapascal, and Poisson's ratio is 0.3. So we want to find the hoop or circumferential stress and longitudinal stress. We want to find our maximum in plane and out of plane shear stresses, and we want to find strains, and also we want to find our stresses perpendicular to this weld line, and also the shear stresses along this line. Okay, all right. So let's solve the example. So these are the given. So alpha is given, R, T, P, E, and Poisson's ratio. So first thing is, since this is a pressure vessel, I can find my hoop stress and my longitudinal stress. So hoop stress is given by PR over T. So when I calculate, I get 80 megapascal. And then I can get my longitudinal stress, which is equal to PR over 2T, which is 40 megapascal. And if after I get these two stress values, then I know that my maximum in-plane shear stress is equal to sigma 1 minus sigma 2 divided by 2, which is equal to PR over 4T, which gives me my 20 megapascal. And the out of plane shear stress, or the maximum shear stress, absolute maximum shear stress, is equal to sigma 1 over 2, which is equal to PR over 2T, which is equal to 40 megapascal. Okay. So for this given pressure vessel, so I find that my maximum stress is 80 and my minimum stress will be equal to 40, and so my in-plane shear stress is, maximum in-plane shear stress is 20, and my maximum out of plane shear stress is 40 megapascal. Okay. All right. And next is, so I want to also find my stresses along this line. Okay. So which means that when I cut it, I will cut a element which has a side of this line. So which means that I need to rotate my element by theta. And here again, this will be my weld line. Okay, so but here this alpha is given. So if this alpha is 60, okay, so which means that, so basically this angle is given. So the angle between my x and this direction. Okay, but I need to find my theta. So basically my theta will be equal to 90 minus alpha, which is equal to 30 degrees. Okay, so just be careful. So this is 30 degrees, but this alpha is given as 60 degrees. And depending on the problem, you might get different values, or they might give you different angles. But the idea is one of this line should correspond to my welding line. Okay, and in this case, I rotate it like this. Okay, so again, I find my theta. Okay, and then I have all my stresses. I know my sigma x, which is equal to 40 megapascal. Okay, so my sigma x is my longitudinal stress in this case, and my sigma y is equal to 80 megapascal. All right, and then what I want to find is basically I want to find this value. So I want to find what's my normal stress. So I want to find my sigma x prime. Okay, and I also want to find what's my sigma y prime and my shear. So I want to find all these values. And how do we find it? So we have the equations. So as long as I know my theta, so I can use this transformation equations. And if you put them there, so you can find that your sigma x1 will be equal to 50 megapascal, your sigma y1 will be equal to 70 megapascal, and your shear stress will be equal to 17.3. And here you get the positive value, so this is why you have tension here, and this is on the positive side. So which means that along this, if you rotate your element by 30 degrees counterclockwise, I will get all the stress values. Okay, and then generally in this question it's not given, but they can give you what is your yield stress, or they can tell you what is the shear stress that it can stand, and then you can compare your values, and then you can determine whether it fails or not. Okay, all right, so let's solve another example. So this is kind of combined stress, combined loading question. So here I have a tensile stress of 200 pounds, and plus a torsion is applied, and also this thin wall pipe has an internal pressure of 500 psi. Okay, and what we want to do is we want to determine the principal stress at a point on the surface of a pipe. So this one, it undergoes tension and a torsion, plus there's internal pressure. Okay, so what I need to do is, so first of all I need to find some properties like section properties. So since the radius is given, the inner diameter is given, and the thickness is given, I can find the area. So it's pi times r of the outer surface square minus r of inner surface square, and you can also find your j given by this equation. Okay, and then we will use our thin wall analysis, and a common practice is generally we check this r over t. Okay, so if this r over t is larger than 10, what we get is our results will be more accurate. If this r over t is small, our results will be a little bit off, because this is a little bit approximation. So when we use our equilibrium, we use a little bit approximation. Okay, all right. So what we want to do is I want to find my normal stress. Okay, and in this case, so when I look at this, so basically I want to find my stress along the pipe direction. Okay, and so I want to find my longitudinal stress, but plus I also have some additional stress due to this applied load. So which means that if I find my stress along the longitudinal direction, it will be equal to n over a plus my longitudinal stress. Okay, so n is 200, and then we already find our area. Okay, and then we know our internal pressure, we know our r, we know our thickness. So from there you can find that your stress, longitudinal stress, is equal to 7.350 ksi. And then I also need to find my hoop stress. So it's just given the equation, it's PR over T. So I just apply the formula and I find that it's equal to 5 ksi. And since I have torsion, what I know is I know that I also have shear stress. And my shear stress is equal to Tc over J. So I know my torque, I know my C, which is the outer radius, divided by J. And just be careful, since we have pound feet, so we also need to convert it to inches. And then if you calculate it, this is your shear stress. So I find my longitudinal stress, I find my hoop stress, and I find my shear stress. Okay, and next is I need to put them on an element. Okay, so sigma x is going to be my longitudinal stress. Okay, sigma y, it will be my hoop stress, okay, and finally I will have the tension. And here the tension direction is important. So if you consider an element on the outer surface, so which direction do you expect your tension to be? If you use your right hand rule, so since, and if I look at from this side, okay, from the end, so this torsion is applied counterclockwise, so which means that actually it creates a shear going downward. So if you cut an element, okay, so you will expect that this shear, due to this torsion, it will go downward. So which means that when you write your stresses, so here I have sigma x, which is tension, I have sigma y, which is tension, but this shear, it will be in the negative direction. Okay, and then you can find your average stress, and so which is equal to sigma x plus sigma y over 2. And then I can also get my radius for my circle. And then if you want to find your principal or stresses, which is maximum and minimum stresses, so it's either sigma average plus r, which will give you 29.4, or the minimum stress, it will be equal to sigma average minus r, which is equal to minus 17 ksi. Okay, so here important things are, so in this question it really doesn't matter much, so whether this shear stress is minus or positive when you find your principal stresses. But for example, if I ask you what are the stresses if you rotate it 30 degrees clockwise or counterclockwise, it might make a difference. So it's also important to determine the correct signs for the stresses. Okay, so don't forget that when you have pressure, so this longitudinal stress and hoop stress, they're always tension. Okay, and this one, it can be tension or compression depending on the applied load. Okay, so in this case this is also tension, so this is why I add them. Okay, and my hoop stress is always tension, so I also get this one. Okay, and depending on how you cut it, so you can determine your axis. So sigma x is longitudinal, and I will say that this is my other direction, perpendicular direction, sigma y, and this is our positive direction. And due to this torque applied counterclockwise, so I will get a minus sign on my shear. Okay, and then rest is find average and r. So if you add them, you will get your maximum. If you subtract them, you will get the minimum.